Welcome to DjamgaMind, your ads-free audio intelligence platform. I'm Etienne Noumen. Today, we strip away the marketing and the metaphors to look at what is actually happening inside a transformer. An LLM does not think, it does not reason, and it does not have intent. It is a mathematical system of weighted sums and nonlinear transformations scaled to a degree that mimics comprehension. Today, we explain the first principles of vectors, attention, and the thermal limits of scaling. No fluff, no ads. Let's dive in.
Welcome to the DjamgaMind special. We are incredibly glad you're here with us for this deep dive. Today, we're bringing you behind the closed doors of the research labs.
Yeah, it's just you and the two of us today. We're sitting down as AI research engineers to pull back the curtain on what we're calling the ghost in the machine.
Right. We are stripping away all the anthropomorphic illusions, all the science fiction narratives, and honestly, all the marketing hype you hear every single day about artificial intelligence.
Our mission for this deep dive is, well, it's pure, unadulterated demystification. We are operating exclusively from a foundational text titled LLMs Explained from First Principles: Vectors, Attention, Backpropagation, and Scaling Limits.
And what we're going to show you, what we really want you to understand by the end of this, is that there's no symbolic reasoning happening in these systems. There's no underlying logic.
No actual comprehension at all.
Exactly. There's only linear algebra, probability distributions, and calculus scaled to a degree that is, well, it's frankly difficult for the human mind to easily grasp.
You often hear people talking about these models as if they have intent. Right, or as if they are actively thinking before they respond to your prompts. The reality, which we will dissect in meticulous mathematical detail today, is entirely dictated by mathematical structure and physical power.
Yeah, so today we're going to walk you through 5 distinct architectural and physical pillars. We're going to start with text as geometry, where we examine how context is formed without a single shred of actual understanding.
Then we'll open up the transformer heart, specifically the query, key, and value systems.
After that, we move into the backprop blame game. That's the massive calculus engine of learning.
We'll follow that up by shattering the memory illusion, breaking down the math of why the machine cannot actually learn about you during a chat.
And finally, we will confront the thermodynamics of the scaling wall, the physical, economic, and material reality of just brute force computation.
By the end of this briefing, you will fundamentally understand why the machine appears intelligent and why it is, at its core, just numbers flowing through a physical substrate.
Okay, let's unpack this, starting at the absolute foundation. Pillar 1, text as geometry. If we're completely stripping away the illusion of a brain, we have to ask how a neural network even processes a word.
Right, because it doesn't.
Exactly. Because a computer running on silicon doesn't read the word apple and picture a piece of fruit. It doesn't process text in any human sense. Everything starts by turning text into numbers. According to our source material, each word, or more accurately, each token, is mapped to a vector.
And a vector is simply a long list of real numbers.
But how do we get from a static list of numbers to something that successfully mimics understanding?
Well, the secret lies in the concept of high-dimensional space. These vectors aren't just arbitrary lists of random numbers. They represent specific spatial coordinates.
Like coordinates on a map.
Yeah, exactly. Imagine a traditional 3D graph with X, Y, and Z axes. Now, instead of 3 dimensions, imagine a space with thousands of dimensions. During the brutal training process, the model slowly shapes where words sit relative to one another in this vast high-dimensional space.
So to understand how it actually does this shifting and shaping, we have to look at the foundational unit of the entire system, right? The artificial neuron.
Right. And a neuron in this context is not a biological cell. It is a strictly mathematical operation. It receives several inputs, and each input is just a numerical value. These inputs might represent an abstract embedding value from our token vectors.
But on their own, these numbers have absolutely no meaning.
None. Meaning only emerges through how the network treats them mathematically.
So what does that mathematical treatment look like? The text explains that each input is multiplied by a weight, and these weights dictate influence.
Correct. A large positive weight means the input strongly pushes the neuron's output higher. A small weight, something near 0, means the input barely matters at all to the final calculation.
And a negative weight pushes the output in the complete opposite direction. So most of what a neural network, quote-unquote, knows is entirely encoded in these specific microscopic weight values.
That's the core of it. Once those inputs are multiplied by their respective weights, the neuron adds all the results together to produce a single number. This is the weighted sum.
But at this exact stage, just adding things up, the neuron hasn't actually made a decision or formed a complex pattern.
No, it has only combined evidence into a raw linear score. And raw scores are largely useless for making sophisticated decisions without some sort of threshold.
Which brings us to the next crucial component, the bias.
Yes, a bias value is added to that weighted sum. You can think of the bias as a threshold offset. It allows the neuron to activate even when the inputs themselves are relatively small. Or, conversely, it forces the neuron to stay inactive unless the combined signal is overwhelmingly strong.
Like a gate.
Exactly. Early neural networks used hard thresholds, literal mathematical step functions that acted as simple on or off switches. Modern networks use smoother mathematical versions of this concept to maintain gradient flow, which we will get to later. But the fundamental role remains identical. The bias is a mathematical gatekeeper for that specific node in the network.
Wait, if the whole architecture is just taking numbers, multiplying them by weights, adding a bias, and summing them up, doesn't basic linear algebra dictate that a massive stack of linear equations just simplifies down to one single basic linear equation?
Yes, it does.
So if it's all just straight lines, how does it actually build the complexity needed to model human language?
This introduces the strictly necessary mathematical architecture known as the activation function. After the bias is added, the result is passed through this function. And this step is non-negotiable for deep learning.
Because it adds the curve.
Right. The activation function introduces nonlinearity. This means the output is not just a straight linear combination of its inputs. As you noted, without activation functions, stacking multiple layers of neurons would be mathematically pointless.
Right. A linear equation plugged into another linear equation just collapses into one single linear equation.
Exactly. The entire massive network, no matter how deep, would have the exact same predictive power as a single layer. So by applying nonlinear functions specifically, the text mentions ReLU, sigmoid, tan, or GELU, the network is permitted to model complex, curved, highly irregular relationships within the data.
So ReLU, for instance, that simply takes any negative number and turns it to 0, while letting positive numbers pass through unchanged.
Yeah. That tiny, simple bend in the math is what allows the network to build abstraction.
It's wild to think that all the nuance of language comes down to bending a straight line.
Yeah.
So what does this all mean for the concept of meaning itself? We are talking about inputs, weights, biases, and activation functions like ReLU or GELU. Nowhere in there is a dictionary. Nowhere in there is a definition of a word or an understanding of grammar. We are completely abandoning the idea of intent. Meaning only emerges through the relative positioning in this high-dimensional vector space.
It is entirely geometric. It is learned over trillions of microscopic mathematical adjustments. When the model associates the token for king with the token for queen, it isn't because it understands royalty or political structures.
It's because the vectors for those tokens have been geometrically positioned near each other and near the vector for gender through brute force statistical mapping.
It is pure geometry, context without a shred of understanding.
Which is fascinating. But that geometry must be processed dynamically, which brings us to our second pillar, the engine that actually manipulates these geometric representations, the transformer heart.
The core math behind the Google Transformer architecture is not symbolic reasoning. It is linear algebra, probability, and calculus arranged in a very specific, highly optimized way.
Right.
From each token vector, the model computes 3 new vectors using matrix multiplication. This is the query, key, and value system, or QKV.
Here's where it gets really interesting. Mathematically, the QKV system is just the token's original vector multiplied by 3 different learned matrices. There's no hidden magic. It's just matrix multiplication.
But the purpose of creating these 3 distinct vectors from one single token is brilliant. It creates different functional representations of the exact same token so it can perform 3 distinct roles simultaneously.
It can ask questions about other tokens using the query vector.
It can be compared against other tokens using the key vector.
And it can carry actual substantive information forward through the network using the value vector.
Let's walk through the exact math attention step by step, because this is the beating heart of the illusion of comprehension. Attention works by taking the dot product between the query vector of one token and the key vectors of all other tokens in the sequence.
And in linear algebra, a dot product measures similarity in a vector space. It is essentially asking, mathematically, how aligned two vectors are in that massive thousand-dimensional space.
Right. If the query vector of the word bank aligns closely with the key vector of the word river, the dot product will yield a very high positive similarity score.
But wait, if we are multiplying all these vast numbers together in the dot product, wouldn't the numbers just explode into infinity and completely break the system?
Hmm.
The text notes that these similarity scores are then divided by the square root of the vector dimension. That feels like a very specific, almost hacked-together step.
It's a critical numerical stability trick. If you take the dot product of two vectors with a high number of dimensions, the variance of the resulting score scales up with the number of dimensions.
So the numbers just get too big.
Exactly. The numbers grow too large, and when we pass them to the next mathematical step, the gradients vanish, meaning the network stops learning entirely. So we scale them back down by dividing by the square root of their dimension. It keeps the numbers well behaved.
And once they're scaled, we apply the softmax function.
Right.
So we have these raw, scaled similarity scores. Some might be positive, some might be negative. How do we turn that into something the network can actually use to weigh information?
Softmax converts those raw, unconstrained scores into probabilities. Mathematically, it takes the natural base e and raises it to the power of the input value. Exponentiation is key here because it takes small differences in the raw score and blows them up.
Making the rich richer, mathematically speaking.
Exactly. If one token has a slightly higher similarity score than another, exponentiating it makes that slightly better token dominate the mathematical space. Then it divides each exponentiated score by the sum of all the scores.
Which ensures that all the resulting numbers are positive and, crucially, that they all sum to exactly 1.0.
This mathematical operation turns raw spatial similarity into a strict distribution of attention. It defines exactly what percentage of focus each token gives to every other token in the sequence.
Okay, so once those probabilities are computed and they all sum to 1.0, we finally use our third vector, the value vector. The probabilities from the softmax are used to take a weighted sum of all the value vectors. The result is a brand new vector for each token that mixes information from other tokens, weighted entirely by that statistical relevance we just calculated.
This is the mechanical reality of how context is formed. Every single token becomes a blend of other tokens, rather than being processed in strict isolation.
So the word bank sitting next to river becomes a mathematically different vector than the word bank sitting next to money.
Because it is a mathematical blending of spatial coordinates. But doing this just once wouldn't capture the complexity of human language. Language has syntax, it has semantics, it has long-range dependencies. A single attention mechanism would just blur everything together into an average.
So to solve this, the transformer uses multi-head attention. This is often considered the secret sauce of the architecture. Multiple attention operations run in parallel.
Each head has its own entirely separate set of learned projection matrices for queries, keys, and values. Because they are initialized differently, each head looks at the exact same sequence of text, but learns to track entirely different patterns in the high-dimensional space.
So one head might focus purely on local syntax, looking at the immediate adjacent words.
And another head might track long-range dependencies, mathematically linking a pronoun back to a specific noun from 3 paragraphs ago.
And after all these parallel heads do their independent math, their outputs are concatenated, just literally stuck together end to end, and pass through yet another matrix multiplication to mix them all together.
Again, basic linear algebra applied repeatedly and in parallel.
But wait, we're talking about sequences of words, and transformers process everything simultaneously in massive parallel matrix multiplications. By their mathematical nature, they have no built-in sense of time or sequence. How does the model mathematically know that the dog bit the man is different from the man bit the dog if it just processes all the words at the exact same time?
That is a fundamental flaw in the raw attention mechanism. It treats text as a bag of words rather than a sequence. Positional information must be injected manually into the vectors before any of the attention math happens.
The original Google design introduced sinusoidal positional encodings, right?
Yes, they use literal sine and cosine functions at different frequencies to inject position into the token vectors in a smooth, continuous way. Mathematically, this is closely related to Fourier features and signal processing.
The low frequencies handle long-distance positional relationships, and the high frequencies handle the precise ordering of adjacent words.
Exactly. It ensures that the geometry of the vector changes slightly depending on where the token sits in the sequence, allowing the model to generalize to longer sequences smoothly without losing track of sequence order.
So we have multi-head attention blending all this context based on position and similarity. But we still need to stabilize this deep stack of mathematical operations. After the attention mechanism, each token is passed through a feed-forward neural network independently.
This network consists of a linear transformation, a nonlinear activation function like the GELU we discussed earlier, and another linear transformation. It increases the expressive power by letting the model reshape the information non-linearly.
But as you stack dozens or hundreds of these layers on top of each other, you risk the numbers either degrading to zero or exploding into infinity, right?
To make deep stacks of these transformer layers physically trainable, residual connections and layer normalization are strictly necessary.
In a residual connection, the input to each sublayer is essentially routed around the math and added back to its own output.
You are literally adding the original vector to the newly processed vector. Then that combined result is normalized, bringing the mean of the numbers to 0 and the variance to 1.
This architectural choice stabilizes the gradients and prevents mathematical information from degrading as it flows through hundreds of layers.
Without residual connections and layer normalization, deep transformers would mathematically fail to train. The signal would just vanish in a sea of matrix multiplications.
So what does this all mean so far? We have mapped out the architecture. The text is high-dimensional geometry, the artificial neurons with weights and biases, the multi-head attention using dot products and softmax to blend vectors, the positional encodings acting as a clock for the sequence, and the residual connections keeping the math stable.
But an architecture is just an empty engine.
Right. Out of the box, it's completely dumb. The weights are just random numbers. It doesn't know anything until it is trained. How does this massive, mathematically complex system actually figure out what those billions of weights should be? How does it learn from its mistakes?
It learns through backpropagation, which we can define fundamentally as the backward assignment of blame.
The blame game.
Yes, the blame game. To understand this, we have to contrast the two main phases of operation during training, the forward pass and the backward pass. In the forward pass, the input goes into the network, flows through all the matrix multiplications, attention heads, and activation functions we just described, and the network makes a prediction.
It outputs a probability distribution over what the next token should be, using a final softmax layer over the entire vocabulary.
For example, it might predict that the next word is cat with a 70% confidence, dog with 20%, and car with 10%.
But during training, we have the actual document. We know what the actual next word in the text is. So we compare the network's prediction to the correct answer. We measure exactly how wrong the network was.
That measurement of error is mathematically defined as the loss, specifically using a cross-entropy loss function.
Now we have a solid mathematical representation of how wrong the network's guess was. So how do we fix it? We have to send that error back.
This is where the calculus comes in at an immense, almost terrifying scale. Backpropagation uses the chain rule of calculus to calculate the gradient for every single weight in the network, starting from the final output layer and moving all the way back to the initial embeddings.
And a gradient is simply a measurement of sensitivity. It tells us exactly how sensitive the final error is to a specific weight.
It answers the question, if I nudge this one specific weight value in this one specific matrix by a microscopic fraction, will the total error go up or down, and by how much?
The mechanical intuition here is beautifully simple, even if the scale is mind-bending. If the calculus says that increasing a weight increases the error, the system pushes that weight's numerical value down.
If increasing a weight decreases the error, the system pushes that weight's value up. The size of that push is determined by the gradient.
That backward assignment of blame, calculating exactly how much every single parameter contributed to the error and adjusting them to reduce that error, is what backpropagation actually is. It's walking down a massive, high-dimensional mountain range of error, trying to find the valley.
What's fascinating here is that this single mathematical process is the entirety of the system's learning. You will often hear the phrase, backpropagation plus gradient descent equals learning.
Gradient descent being the actual process of updating the parameters slightly in the direction the gradients suggest.
Exactly. This exact cycle forward pass, calculate loss, backward pass to calculate gradients, update weights via gradient descent, is repeated trillions of times. The model never understands why those specific mappings of inputs to outputs work.
It never grasps the concept of a cat or a dog.
No, it is simply optimizing a large collection of numbers to statistically reduce error on past data.
It's wild to think we're burning the energy equivalent of a small city just to do basic calculus on steroids.
Yeah.
We need to emphasize the sheer compute brutality of this process. It is hard to overstate.
It really is. For every single token in the training data, The model must perform the forward pass, compute the cross-entropy loss, and then perform the brutal backward pass.
And that backward pass must touch billions or even trillions of parameters. It requires massive matrix multiplications. It requires extremely high numerical precision.
This is exactly why traditional computer processors, CPUs, would take centuries to train a modern large language model. They just can't do the parallel math fast enough.
It requires the highly parallel architecture of GPUs, graphics processing units, or TPUs, tensor processing units, which are designed specifically to perform thousands of matrix multiplications simultaneously.
This compute brutality is the reality of the mathematical structure. The system is highly efficient at statistical approximation, but it is utterly devoid of causality or reasoning. It does not build an internal, logical model of the world that it updates with new information.
It simply maps inputs to outputs based on historical gradient descent, which perfectly segues into our fourth pillar, the memory illusion and the mathematical inevitability of catastrophic forgetting.
Right.
We all see the chatbot apologize and think it's adapting to us. When you sit down and open a chat window with a frontier model, you type in a prompt. The model responds. You correct it. It says, "I apologize, you are correct," and adjusts its next answer.
It feels exactly like you are teaching it.
It feels like it is learning about you, adapting its worldview based on your conversation. But when you look at the matrix math happening during that inference phase, is it actually learning anything permanent?
It is entirely an illusion. Once a model finishes the massive, computationally brutal training phase we just described, all of its weights are fixed. The matrices are locked.
It cannot modify those numbers during your conversation because backpropagation is turned off.
It cannot store new memories in its parameters. It cannot integrate new facts into its core architecture. It cannot update its world model. What you are experiencing as a user is a temporary illusion called in-context memory tracking.
Right, because of the attention mechanism we talked about in Pillar 2. The model is using the multi-head attention to look back at the words currently sitting in the chat window, the context, and blending those tokens to predict the next word.
It is mathematically conditioning its output on the provided context in real time. But the moment you close that session or the moment the text exceeds the model's maximum context window, all of that learning simply evaporates.
It vanishes into the ether. The underlying weights of the model haven't changed by a single decimal point.
You might ask, well, why not just update the weights? If the model gets a fact wrong, why can't we just find the memory cell where that fact is stored and change the weights related to that one fact using a quick burst of backpropagation?
Which brings us to the distributed knowledge problem. Targeted learning is mathematically nearly impossible without full retraining because knowledge in a neural network is distributed, not localized.
There is no single memory cell for a fact. Let's use the text example. The concept of gravity. Gravity isn't stored in one specific artificial neuron that we can just go in and edit.
The concept of gravity activates billions of parameters across the network, and those exact same parameters are heavily intertwined and overlapping with the representations for apples, Newton physics equations, and a million other concepts.
Everything is a holistically encoded blend in that high-dimensional vector space. It's a massive superposition of concepts.
Because of this distributed, overlapping geometry, you cannot safely isolate updates. If you try to force the network to adjust its weights to learn one new specific fact, you cause mathematical ripple damage across the entire system.
Because neurons are shared across millions of concepts, changing one weight to fix a fact about gravity might accidentally alter the network's mathematical pathways for how to format a Python script or how to conjugate a French verb.
This phenomenon is known as catastrophic forgetting.
Yes.
Catastrophic forgetting. It's the ultimate irony of AI engineering. You spend $100 million to train a model and try to teach it some new laws of physics, and it suddenly forgets how to code in Python as a result.
New learning actively overwrites old representations. The model simply forgets previous skills or facts because the overlapping geometric space gets distorted by the new gradient updates.
The text explicitly notes that unlike human brains, neural networks do not naturally protect old knowledge. They just ruthlessly optimize for the new gradient update, destroying anything that gets in the way of reducing that specific localized error.
The text does mention that engineers attempt to mitigate this using parameter-efficient fine-tuning, or PEFT. Techniques like LoRa, low-rank adaptation, try to solve this by only tweaking a very small, isolated subset of parameters, or adding small adapter layers on top of the frozen model rather than updating the entire massive network.
But even these techniques do not fully solve the fundamental mathematical isolation problem. They are band-aids. The core architecture simply does not support the isolated storage of discrete facts.
So to genuinely teach the model a substantial amount of new information, you can't just chat with it and you can't just tweak a few parameters with PFT. You have to undergo the brutally expensive, massive training process again.
Which brings us directly into our fifth and final pillar, the scaling wall. The thermodynamics, the economics, and the physical limits of brute force computation.
We constantly hear narratives about AI inevitably taking over the world, assuming an exponential, unstoppable curve of intelligence that will just keep rocketing upward. But there is a very real, very physical wall we are hitting.
We need to redefine what training actually is at this scale. As we established, it is not learning concepts. The core task an LLM performs during training is brute force statistical compression.
It is constantly asking one single mathematical question over and over again. Given everything I've seen so far in the sequence, what token is most likely next?
To make that statistical compression work, you have to show the model trillions of tokens. You have to calculate the softmax probabilities across tens or hundreds of thousands of vocabulary possibilities, and you have to repeat the backpropagation calculus, nudging billions of parameters by microscopic amounts, trillions of times.
The text is blunt. There are no shortcuts here. It is raw numerical grind. And here is the harsh economic reality. The scaling costs are highly nonlinear.
What actually improved model quality over the last several years wasn't some hidden algorithmic breakthrough in the mathematics of logic. It was scale. More parameters, more data, more compute.
But a 10x gain in capability or model size does not cost 10x more money. According to the text, once you factor in the physical realities of the hardware, it can easily cost 20x to 40x more.
Let's look at those hidden overhead costs, because this is where the physics of the real world drag the math back down to earth. First, memory limits. These frontier models are so massive, they physically cannot fit on the RAM of a single GPU.
So the model must be sharded, broken apart across thousands of different accelerators.
Second, interconnect bandwidth. Because the model is shattered across thousands of chips, those chips have to constantly talk to each other over networking cables like NVLink or InfiniBand to share the matrix multiplication results.
At these scales, the sheer movement of data back and forth across physical cables hurts almost as much as doing the math itself. The GPUs spend huge amounts of time just sitting idle, burning power, waiting on memory transfers from another rack across the data center.
And third, the synchronization overhead. Just keeping thousands of accelerators synchronized, ensuring that the gradient updates from one shard perfectly match the gradient updates from another, burns enormous amounts of power.
The text explicitly states that training frontier models is no longer a compute-bound problem. It is an infrastructure-bound problem. Furthermore, we must address the realities of infrastructure failures. People rarely talk about how often these massive training runs simply fail entirely.
Hardware faults happen constantly when you are running 10,000 GPUs at maximum thermal capacity for 3 months straight. Chips literally burn out. Cosmic rays flip bits in the memory. Thermal throttling kicks in.
NANDs happen, not a MOMER, number errors where the calculus results in an infinity or an undefined value, completely ruining the mathematical stability of the entire network instantly.
Runs diverge, meaning the loss suddenly spikes into the stratosphere instead of going down. Hyperparameters, the manual settings the engineers choose before starting the run, like the learning rate, turn out to be slightly wrong.
Massive training runs are frequently restarted multiple times, and every single restart costs millions of dollars in electricity and wasted compute time.
To give you a realistic order of magnitude view stripping away the marketing numbers, we are looking at a $1 trillion trajectory. The text lays out the historical context clearly. Early generation large language models cost roughly $10 to $50 million to train.
They utilized about 10 to the 24th power FLOPs, floating point operations, using thousands of GPUs for a few weeks.
Fast forward to the current frontier models. Those cost more like $100 to $300 million just for the compute. We're looking at 10 to the 25th power FLOPs. That requires 10,000 plus accelerators running constantly for months.
And the next generation. The text projects those will very likely cost $500 million to over $1 billion strictly for a single training run. That is 10 to the 26th power FLOPs.
We are talking about entirely dedicated data center scale operations with the total power consumption comparable to a small town. And remember, that $1 billion is just for the raw pre-training. That doesn't even include the fine-tuning, the safety training, the red teaming, or the deployment optimization.
This brings us to the tension between scaling laws and physical reality. Over the last few years, researchers documented these scaling laws. They found that when you increase model parameters, training data, and total compute, the training loss decreases in a smooth, predictable way that strictly follows a power law.
Let's define that power law mathematically. The loss is proportional to compute raised to a small negative exponent, and the text specifies that exponent is very small, something like 0.805 to zero point 0.1.
In practice, this means every tenfold increase in compute gives a consistent, measurable improvement in lowering the loss. It isn't random. It isn't chaotic jumps in intelligence. It is a smooth mathematical gain that follows a curve.
This power law is the entire foundational argument for the just keep scaling philosophy. Historically, it has worked perfectly.
This raises an important question, though. Power laws have diminishing returns mathematically built right into them. Because that exponent is so small, 0.05 to zero point 0.1, every additional tenfold increase in computational power produces smaller and smaller real-world gains.
The curve keeps improving, yes, but it inevitably flattens. There is no sharp mathematical cliff, but there is a clear pattern of increasingly expensive microscopic improvements. You can't keep pushing the scale, but the financial and energetic cost grows exponentially rapidly compared to the linear benefit.
And beyond the mathematical diminishing returns, we hit the data wall. This mathematical scaling law assumes you have an ever-increasing supply of high-quality training data. But high-quality, human-generated text on the internet is finite.
We are rapidly approaching the point where models have already consumed the entirety of the high-quality internet. Every book, every article, every Wikipedia page.
To keep scaling, engineers are relying on synthetic data generated by other AI models, or lower quality data, or multimodal sources like video and audio. If the quality or diversity of this new data stops increasing, the fundamental math of the scaling relationship might weaken. The curve could shift or plateau entirely.
Thermodynamics always collects its due. The reason costs keep rising instead of falling lines up perfectly with physical reality. Compute lives in matter. Matter wears out. Energy is not free.
We cannot simply rely on hardware getting exponentially more efficient anymore. Transistors cannot shrink forever. They're already approaching the size of individual atoms. Memory bandwidth becomes a strict physical bottleneck. Moore's law, the historical observation that computing power doubles while costs halve every 2 years, is effectively dead.
Brute force replaced Moore's law. Every new model generation is basically the AI industry saying, spend more money, burn more hardware, secure more nuclear power plants, and hope the mathematical scaling power law still holds.
The uncomfortable truth is that these systems are fundamentally limited by physics, not software cleverness. They improve by throwing billions of dollars of capital and literal town-sized energy grids at the mathematical problem of statistical compression.
Skepticism about this trajectory is not irrational. As our source text argues, it is deeply grounded in thermodynamics and material reality.
The math shows that scaling has produced improvements within the tested regimes, but it does not prove that infinite autonomous intelligence will emerge from scaling alone. We are on a smooth but flattening curve, bound entirely by the physical limits of hardware and energy.
Let's synthesize everything we have covered in this deep dive. We've traveled from the microscopic to the macroscopic. We started with tokens mapped into high-dimensional vector geometry, flowing through artificial neurons, calculating weighted sums, and nonlinear activations like ReLU.
We broke down the Google Transformer heart, revealing that context is just query, key, and value matrices, generating dot product similarity scores, mathematically stabilized by softmax distributions and residual connections.
From there, we exposed the engine of learning itself, backpropagation. The brutal, massive-scale calculus that uses the chain rule to assign backward blame and adjust billions of weights via gradient descent.
We shattered the memory illusion, proving that without retraining, a model's weights are locked, making true learning in a chat window impossible due to the distributed nature of the parameters and the mathematical inevitability of catastrophic forgetting.
And finally, we zoomed out to the scaling wall. The reality that this mathematical architecture is fundamentally a brute force statistical compression engine, tracked by power laws, diminishing returns, finite human data, and the strict thermodynamic limits of silicon and electricity.
We have pulled back the curtain on the ghost in the machine, and what we found is that intelligence in these systems is an illusion born purely of scale and data, not comprehension or agency. It is, from top to bottom, a mathematical system mapping inputs to outputs.
We must look at the fundamental objective of this entire trillion-dollar infrastructure before we close. We want to leave you with one final, provocative thought to mull over, grounded strictly in the final paragraphs of our source text. The text notes that these massive language models are optimized by backpropagation for one singular objective: to lower the cross-entropy loss by predicting the next token. That is it. The math adjusts billions of weights solely to get better at guessing the next word in a sequence.
But lowering this specific mathematical loss does not automatically optimize for long-term planning. It does not optimize for persistent memory. It does not optimize for grounded reasoning or autonomous agency.
Consider this. If the entire multi-billion-dollar, power-hungry infrastructure of the AI industry is fundamentally built on a mathematical objective that simply guesses the next word, are we trying to build a skyscraper on a foundation meant for a shed? No matter how many GPUs we daisy-chain together, no matter how many gigawatts of power we burn to make the next token prediction statistically flawless, the math itself might physically prevent true autonomous reasoning from ever emerging from this specific architecture.
You cannot scale a mathematical formula into a capability it wasn't designed to measure.
Thank you for joining us for the DjamgaMind special. We hope this deep dive into the math, the architecture, and the physics has demystified the machine for you. Until next time.
That concludes our DjamgaMind special on the first principles of LLMs. The signal for today is numerical brute force. Intelligence in its current synthetic form is a byproduct of scale and statistical approximation, not symbolic logic. Understanding this reality is the only way to navigate the plateau that lies ahead. Thank you for supporting independent, ads-free audio intelligence. I'm Etienne Noumen. Until next time, stay sharp and keep unraveling the future.